up to now we have discussed the introduction of the complex compounds or the coordination compounds. Like what is a complex, how the complex we can differentiate from the normal salt, okay, and also what is the basic idea about the complex compounds or the coordination compounds, like what is a coordination number, what is a ligand, okay, what is a metal atom. There are things what we discussed up to now. Now let us go for further details in the particular chapter. We'll start with Werner's theory. Yeah, this theory explains about exactly what is a complex and how the complex we can differentiate or indicate. So in order to explain this, Werner have considered the cobalt amine complexes. Let us see the main points of particular Werner's theory. The first one is, if I take a metal or the complex compound, the complex compound will associate with one central metal atom or central metal ion. The central metal atom or central metal ion will have the two types of valencies. One is primary valency and the second is secondary valency. So here there should be one central metal atom or central metal ion in the complex compound. It will possess two types of valencies, primary valency and the secondary valency. Generally, the primary valency is the oxidation state of the central metal atom or central metal ion. So oxidation state. Oxidation state of central metal. And coming to the secondary valency, this secondary valency tells about the number of ligands or number of bonds or coordinate covalent bonds that are present between the central atom and the ligands. This will tell us about the coordination number. Of course, we can also say this is the number of ligands. And here we are saying the primary valency as the oxidation state of the central atom. So generally this primary valency will be satisfied by or neutralized by the anions, because here oxidation state of the central metal. So metal always shows positive oxidation state. So this will be satisfied by generally the anions here, so that the resultant complex will be neutral. Okay, and but coming to the secondary valency, the secondary valency can be satisfied by the ligands. So here already we discussed the ligand can be positive ligand, the negative ligand, or the neutral ligand. For example, the positive ligand like N2H5 plus hydrazine ion. Okay, and also negative ligands like Cn minus, cyanide, the neutral ligand like CO, carbon monoxide. So here the secondary valency can be satisfied by either positive ligand or negative ligand or the neutral ligand. But coming to the primary valence here, that is satisfied only by the corresponding anions, because it is the oxidation state, no? So compulsory metal is a positive, generally electropositive element. That's why for the metal it will be positive oxidation state. So definitely it should be satisfied by the corresponding anion only. So generally, in order to understand this particular concept, Werner have considered the corresponding cobalt amine complexes. So for example, CO NH3 taken 6 Cl3. So in this case, here as per the discussion, so central metal atom is actually cobalt here. The oxidation state of the cobalt is +3. That means here the primary valency of the corresponding metal is plus 3, or the complex is plus 3 here, primary valency for the corresponding metal. Okay, and it is having positive charge, so definitely that should be satisfied by the negatively charged ions, which are chloride ions. So in this particular case, chlorides are satisfying the counter ions, because if you split this here, arrow above this will get the positive charge from the complex, so this is satisfied by the anions only. The same time, coming to this, so this is a coordination number 6. That means to say here, around this cobalt we can have 6 ammonia molecules. Each ammonia will provide one lone pair of electron to the central metal atom. That means around this we can see here the 6 ammonia molecules. That's why in this particular complex the secondary valency of the metal is 6. The secondary valency is 6. That's why, see, as per the discussion I told you here, the coordination number, or simply we can say the secondary valency can be satisfied by the neutral molecules like ammonia, water. Here I told you carbon monoxide, NO. All this can satisfy the secondary valency. But particularly, you have considered the cobalt amine complexes in order to explain the corresponding complexes according to the Werner. Okay. At the same time, while representing the corresponding complex, generally in order to show the secondary valency, we have to show with this kind of the lines, dark line. If it is a primary valency, we have to show like this. And the ligands what we are showing here generally can satisfy both primary as well as secondary valencies. Suppose if you take particularly here we have chloride ion in this example. So this chloride can satisfy both primary as well as secondary valencies. Not only primary valence, it can also satisfy the corresponding the secondary valency also. So that's why these complexes we come across, we can have different kinds. Like the first kind I told you here, this is COCl3.6NH3. And you can also use here COCl3.5NH3. And we can write COCl3.4NH3, and also COCl3.3NH3. So in this first case, here the 6 ammonia molecules we have, these 6 ammonia molecules will satisfy the secondary valency of the corresponding metal. And coming to, we have 3 chlorides here. So these 3 chlorides satisfy the primary valency. But in the second case, see here, we have only 5 ammonia molecules here. So whenever we come across the second complex here, the ammonia will satisfy the secondary valency, and among these 3 chlorides, 2 will satisfy only primary valency, remaining 1 chloride satisfies both primary as well as secondary valency for this particular second case. And coming to third case here we have 4 ammonia molecules only. So these 4 will satisfy only the secondary valency, but out of these 3 chlorides, 2 will satisfy both primary as well as secondary valency. The remaining third one will satisfy only the primary valency for the corresponding complex. And coming to the last case here, we have 3 ammonia molecules. So these 3 ammonia molecules, if I come across, satisfies only the secondary valency, but coming to the chloride, we have 3 chlorides, no? So that's why these 3 chlorides satisfy both primary as well as secondary valency. So these we can represent just by drawing the corresponding structures. Just continuation. Yeah, let us see here. The first complex I told you here, that is COCl3 6NH3. So as per this representation, here the 6 ammonia molecules will satisfy only the secondary valency, but coming to 3 chlorides, they will satisfy only the primary valency. The same we can show like this. So this is the cobalt, this is primary valency of this corresponding ammonia molecules, secondary valencies. This is also secondary valency for the ammonia, which is satisfying the complex or central metal, and this is also the ammonia. So we have 1, 2, 3, 4, 5, 6. But coming to the chlorides we have. So these chlorides will satisfy only the primary valency. Just for convenience, we are writing like this. Chloride. This is also chloride. This is a chloride. This is how we can represent this particular complex. And coming to the second one, as I told you, COCl3, that is 5NH3. So here 5 ammonia molecules will satisfy only the secondary valency. Out of 3 chlorides, 1 will satisfy both primary as well as secondary, remaining 2 will satisfy only the primary valency. So we can show like this: cobalt, NH3, ammonia molecule. So assume this is another ammonia molecule. We have 1, 2, 3, 4, 5. And coming to the chloride, as I told you, this will satisfy both primary as well as secondary valency. So we have still 2 chlorides. You have to write like this: Cl minus. So always the primary valence we are writing here, try to write away from, little bit away from, like this, central atom, central metal ion. This is the second way of representing the second complex here. And coming to the third one, that is COCl3 4NH3. COCl3 4NH3. That means in this particular complex here, 4 ammonia molecules will satisfy only the secondary. Coming to the chlorides, 2 will satisfy both primary as well as secondary, and the other chloride will satisfy only the primary valency only. That is ammonia, for ammonia molecules, and this is 1 chloride, Cl minus, other chloride, Cl minus. So we have only 2 chlorides. The third one is able to satisfy only the primary valency. This is COCl3 dot 4NH3. And coming to the next one, COCl3 dot 3NH3. That means in this case 3 ammonia will satisfy only the secondary valency. I mean the remaining 3 chlorides will satisfy both primary as well as secondary valencies. That is cobalt, NH3, ammonia. This is assumed as chloride, will satisfy only the corresponding primary as well as secondary valencies. Ammonia only the secondary valency, And coming to the chloride, both primary as well as secondary valency. Again, this is ammonia will satisfy only the secondary valency, and the chloride only coming to this, it can shows both primary as well as secondary valencies. This is how we can show this corresponding complexes with respect to the corresponding awareness theory. This is okay. And apart from this, when we write the corresponding complexes here, if we take the first case here, this is COCl3 6NH3. So as per the representation, that is COCl3 6NH3. Actually, we can write this like this: CONH3 taken 6 Cl3. So when we place this in water, as you are aware, these are also ionic compounds. When we place this in water, we can have a complex cation CONH3 taken 6 3 plus and chloride ions. That's why in this particular example, suppose to the resultant aqueous solution, if we add the silver nitrate aqueous solution AgNO3, we can get 3 moles of the AgCl precipitate, because 1 mole of the complex is able to give us the 3 moles of the chloride ions. That's why if we add excess of the AgNO3 to the resultant aqueous solution of this particular first complex here, we can observe the precipitation of the 3 moles of the silver chloride. That is, the AgNO3 silver nitrate will provide us the corresponding cation and anion. So here we have 3 moles of the chlorides. That's why taking here 3 moles of this will produce 3 moles of Ag plus and 3 moles of the nitrate. That's why, so 3 moles of this Ag plus ions will react with 3 moles of the chlorides to give 3 moles of the AgCl precipitate. So the color of the AgCl, it is the white precipitate. White precipitate. Of course, we are aware this is generally soluble in ammonia solution, because this will form a complex with ammonia solution. So there will get the ammonia and the silver complex, where the coordination number of silver there it is 2. But this is insoluble in water. This is insoluble in water, but it is soluble in excess of the ammonia solution, because this AgCl converts into the corresponding silver ammonia complex. Silver ammonia complex. At the same time, we take the second case. Second one. So as per this representation, the second one we can show like this. That is CONH3 taken 5 Cl2, because as I told you, this chloride will satisfy both primary as well as the secondary valency. So that's why if I take this second complex, now place a second complex in water. So by placing in water, so definitely this will undergo ionization to give the corresponding cation as the complex cation, which is having the charge of +2, and 2 moles of the chlorides will be released. That means from every 1 mole of this complex 2, we can observe formation or release of the 2 chloride or 2 moles of the chlorides ions will be released. That's why if I take this aqueous solution of this solution and add excess of the silver nitrate AgNO3, so definitely 2 moles of this will be precipitated. That's why in the resultant solution here, if you see here, 2 moles of Ag plus will provide 2 moles of the Ag AgCl. 2 moles of the AgCl. This is how we can see the second one. And coming to the third case, here, this is COCl3 4NH3. That is, you can see here, out of 4 ammonia molecules, okay, all will satisfy the secondary valency. That means we can show the complex like this: CONH3 taken 4 Cl2 Cl. So that's why this particular chloride will release into the corresponding aqueous solution. That's why to the aqueous solution of this complex, if we add excess of the AgNO3, silver nitrate, so definitely we can get 1 mole of the AgCl as the precipitate. The reason is 1 mole of this is able to give us the 1 mole of the chloride ions. That's why when we add X of the AgNO3 to the aqueous solution of this, definitely 1 mole of the AgCl precipitate will be formed. And coming to the last case here, so this fourth complex we can represent like CONH3 taken thrice Cl3. So this is actually neutral complex. So this won't release any kind of the chloride ions. That's why if add any X of the AgNO3 to this aqueous solution, we won't get any precipitate of the silver chloride. So this also we can have importance with reference to the stoichiometric. Stoichiometric calculations also generally can be asked in the exam point of view.
If you like this video, please give a thumbs up. Please subscribe to our channel to get more videos on CBSE syllabus.